Hello everyone. In this second video on the third visualization of complex multiplication over imaginary quadratic fields, I'm going to illustrate the method here. First of all, we're going to start with two complex numbers A and B, componentized by their real and imaginary components A1, A2, and B1, B2. Now what we're looking for is, of course, a graphic or visual illustration of this complex product again. It just so happens if we take the complex product A conjugate B, that the real portion of that complex product is going to correspond to the inner or dot product of two corresponding vectors A and B, and the imaginary portion is going to correspond to the component-wise, that's very important, component-wise wedge or outer product of two corresponding vectors A and B. This just shows the correspondence between the vectors and complex numbers. This caret above this vector A here indicates that it's reflected across the real axis. The second component is negated, which corresponds to the conjugate of the complex number A. Down here, if we take the negative of the second component of the first complex number or the corresponding vector, we end up finding that that is going to be equal to the real portion of the original complex numbers A and B. Likewise, if we take the negative of the second component of the first vector and take the wedge or outer product of it, we find out that we come up with a component-wise manifestation of the imaginary portion of the complex product A-B. Now, to give an example of this rather abstract kind of thing graphically would probably be more helpful. So let's get right on to that. What we do, the first thing, we're going to take two complex numbers, 6 plus 2i, or the vector 6, 2, and a complex number 3 plus 6i, or the vector 3, 6, and we're going to find out the complex product of it. First, we're going to reflect the first vector across the real axis corresponding to the conjugate of the first complex number. Then we're going to form the vector sum over here. The vector sum of the reflected vector and the second vector, second complex number, in relation with the origin. Then we're going to form the parallelogram of this from the origin out to the conjugate, or the reflected vector, up to the sum of the two vectors, and over to the terminus point of the second vector, second complex number, back to the origin again, and then we've got our parallelogram. Okay. Now, the direction in which we take the vertices is determined because we always have to take the conjugate or the reflected vector first. So that forces us around. In this case, forces us around the vertices in the counterclockwise manner. Therefore, we know that the sign associated with that wedge or outer product is going to be positive, and therefore the imaginary portion here of this product of A and B, of these two vectors, is going to be these two complex numbers is going to be positive. What we did there was we took a perpendicular to the reflected vector through the terminus point of the second vector. That is the conjugate of the first complex number, perpendicular to that through the terminus point of the second complex number, or the second complex number. Now we have to determine the intersection point of this reflected vector and this perpendicular line. There we go. And then we have to determine some distances here, distance or length. First, we're going to calculate the magnitude of the reflected vector, which is, of course, the same as this vector 6, 2 up here. Then we have to calculate the distance here from the terminus point of this vector or that complex number down to the projection of that vector onto this reflected vector, which corresponds to the height of the parallelogram. Okay, then we're going to calculate the distance from the point to this intersection point along the reflected vector, which corresponds to the projection of this vector here, the second complex number, onto the conjugate or the reflection of the first, the reflected corresponding reflection of the corresponding vector of the first complex number over here. Now we have sufficient information to calculate our inner and outer products. For reasons will become apparent when we consider some of the other imaginary quadratic fields, because with some of them, with all of them, there needs to be an adjustment to this method, and for some of them it's easier to calculate the imaginary portion first. So that's what we're going to do here. First, we're going to calculate the imaginary portion. We're going to start with this base of this parallelogram, the 6.32. We're going to multiply it by this height, 6.64. As we determined before, because we're taking the vertices of this parallelogram in a kind of clockwise fashion, we know that this area is going to be positive, and therefore the imaginary portion of our complex product will be positive. We come up with the number 42, which corresponds with the imaginary portion of our complex product. Then we're going to calculate the inner product, which again we know is positive because it's on the positive, whatever, it's positive. It's within the original vector here that we're taking in that formula I gave before. It's the projection of the second vector times the magnitude of the magnitude of the projection of the second vector onto the first vector times the first vector, if you will, the magnitude of the first vector. And since it's over here as opposed to over here, it's positive. If it was over here further or translated this, it'd still be positive. As long as it's the original vector or positive translate of it is positive. If it's a negative translate, then of course it's negative, the inner product. Yeah, I hope most of you have seen the first video anyway. So we know it's going to be positive, so we're just going to multiply the magnitude of the reflective vector times the projection of the second onto it, and we come up with 6 for the real portion. Now we're just going to check that against my calculations here, and in fact 6 plus 2i times 3 plus 6i, we came up with 6 for the real portion and 42 for the imaginary portion. So that does in fact check out. Another way to determine the signs, which is very easy, I'm not sure I showed in the first video, was you can define some new axes. Well, actually I got to define a parallel line first. A line that's going to be parallel to this, perpendicular to the reflected vector through the origin. Okay. Then we're going to define some new axes here. Of course, origin, sort of the real portion of it, or the horizontal axes, well, relatively horizontal, will be along the reflective vector, and the second one's going to be along this perpendicular to that reflected vector to the origin. Now, basically what it is that this point here, the intersection point here, will of course tell us about the sign of the real portion of the complex product in relation to these superimposed axes. If it's on the right-hand side of this vertical axis here, then we know that the inner product and correspondingly the real portion of the complex product will be positive. If it's on the left-hand side here of this vertical axis, then we know the inner product will be negative, and that the real portion of the complex product will be negative also. With this point up here, the intersection point, the terminus point in this perpendicular line we drew through the reflective vector, this 3, 6 up here, or 3 plus 6i. Okay, this point in relation to these axes will tell us the sign of the imaginary portion of the product, okay, or the sign of the of this parallelogram. Okay, basically, if it's above this axis, above this horizontal axis, the imaginary portion, the sign of the parallelogram will be positive, and the sign of the imaginary portion of a complex product will be positive. If it's below this horizontal, well, sort of horizontal, superimposed, sort of horizontal axis, then it will be negative. That's another way of telling the sign. And oftentimes, you can just look at it, you don't have to draw the axes, and you know just where they are. And so I'll show you some shorthands in a later video, because I'm sure we're running out of time here, how we can use that. And most of the time, unless it's really close to where one of those axes would be, you can just tell with looking at it without having to draw the axes themselves, what the signs of the two imaginary and real, what the sign of the real and imaginary portion will be. Anyway, this is probably getting close to 10 minutes, so I've got to stop now.